everyone, it's Mr. Hamilton here. In this question, we're going to find all the roots and graph the function of the degree 6 polynomial shown. Now, the first thing to note is that the coefficient of the first term is -2. So all the other terms are also even. So I'm going to go ahead and I'm going to factor out that -2. It's just going to make it a little easier to find possible rational roots. And so I can divide all the terms by 2 and switch the signs because the negative will switch all the signs. And I'm left with the following. So now what I can do is I can focus in on the first coefficient on the first term and then the last term. The first term, the coefficient of it is q, and the last term is p. And what I'm going to do is I'm going to list factors of those to find the possible rational roots. So the factors of p are plus or minus 1, 2, and 4. And the factors of q are just plus or minus 1 because it's just a coefficient of 1. So to find our possible rational roots, we then go p divided by q. So that's just divided by 1, so it's plus or minus 1, 2, and 4. Those are the only possible rational roots that we can have. We can't have 3, we can't have 5, only 1, 2, and 4, and the positive and negative of those. Which brings us now to the Descartes rule of signs. So the first thing we do here, just to introduce this idea, is we look at f of x and we see how many times the sign changes from positive to negative, from negative to positive, all the way along. And we can see there we have one sign change from the x to the 5th to the x to the 4th. That should say a little 4 as an exponent after the 6x. And then another sign change to the x cubed term, and then another sign change to the x term. And so we have 3 sign changes total here. And so what that means is that we can have maximum 3 positive rational roots. And so what we're going to see now is if we do the negative x case. So if we subbed in negative x for all the terms, all the odd exponents, that means the signs are going to switch because a negative to a odd exponent is going to make the sign switch. So we're going to have that now be positive in front of the x to the 5th term. The x to the 3rd term is going to become positive as well. And then the x term is going to also become opposite, which is now going to become negative. And so there are the 3 sign changes that we've experienced, but how many times does it change now as we read it from left to right? Well, it changes from the power of 6 to the power of 5, power of 3 to the power of 2, and the power of 1 to the power of 0. And so that means we have 3 sign changes on the negative x case, and so that means we have a maximum of 3 negative roots. So now we build a chart based on this. We have a positive column, a negative column, complex roots column, and then the total. We're going to have 6 total roots, and if we had 3 positive and 3 negative roots, we couldn't have any complex roots. And the reason we have 6 total roots is because it's degree 6. We could also go down each of the positive and negatives by 2, not by 1, but always by 2. And complex roots always come in pairs. So we could have 3 positive, 1 negative, 2 complex, 1 positive, 3 negative, and 2 complex, or 1, 1, and 4. Now that last case is really, really hard to solve. We don't have the tools to do that at this point, so we're not going to run into that. But we're going to go ahead now and use our possible rational roots, plus or minus 1, 2, and 4, to actually determine what are the roots. And so one of the really cool things we can do here is we could use what's called the remainder theorem. If we sub in one of the possible rational roots, and that just gives me something that's equal to 0, what that means is that that is a root. So in this case, if I subbed in positive 1, and you can see how I've done that into each of the terms, when I simplify everything and bring it all together, which you could do quickly on your calculator as well, I find that this ends up giving me 0. And so what that means is it means that 1 is a root. And so we're going to use that in a moment to divide that using something called synthetic division into that degree 6 polynomial to simplify things for us. If we do the same thing with negative 1, we also get 0. So that means that negative 1 will also be a root. So with those 2 things in hand, let's go ahead and begin using synthetic division to do this. And so what we do here is we write the coefficients of what's in the brackets here because we've common factored out the -2. So that's not really relevant to what we need here. So we're focusing in on the brackets, and the coefficients are 1, 1, -3, 1, 6, -2, and -4. And now we can carry out the synthetic division. Now we do that by first putting a 0 in that place. We go 1 plus 0 is 1. And then we multiply the number out front by 1, and then we add it in the next column. We get 2. We multiply that by the number out front of 1. 2 times 1 gives me 2. Add it again. Multiply by the number in front. -1 times 1 gives me -1. Add it to the 1 above it. get 0, and we carry that pattern on over and over and over, and what we find, as we would have expected, because we used the remainder theorem to sub in 1 into the equation earlier, we get a remainder of 0. So just to reiterate that this is called the synthetic division, and the remainder, in this case being 0, means that 1 is a root. So in general, if we get 0, what that means is that that is a factor. So in this case, if the root is 1, that means x minus 1 would be a factor. So I'm just showing you how that works. Because x is 1, that means x minus 1 would be equal to 0, which when we put that in factored form would be x minus 1. So x minus 1 is a factor. And so what do those numbers mean now that we're left with? Well, those mean the coefficients now of a 1 less degree function, so a degree 5 function. So those are the coefficients of x to the 5th plus 2x to the 4th minus 1x cubed plus 0x squared plus 6x plus 4. And so what that means is if we were to pull out that first factor, it means negative 2 times that factor we found of x minus 1 times that degree 5 polynomial. And we're going to carry this on again and again and again until we get this down as low as we can, and hopefully we can do something with maybe a quadratic or something like that. So the number we write in front is called a root, and then we put it with like x minus 1 like I did on the right there, that's called the factor. So we're now going to try the root of 1 again. So we're going to take 1 and we're going to use synthetic division just like we did before. 1 plus 0 is 1, 1 times 1 is 1, add it up 3, 3 times 1, put it there, add that up 2, 2 times 1 is 2, write that below 0, add that up 2, and carry that on again and again. And unfortunately in this case, it actually does not work out. And so what that means is that that factor of x minus 1, or that root of 1, is only one root. It's not a double root, it's not a triple root, it only exists once. And so now what we're going to do is we know that negative 1 works. We did that to show that with the remainder theorem by subbing that into the equation on the last picture you saw. And so let's go ahead and use negative 1. We know that works, and so let's see what the remainder ends up being when we do that. So again, the same process. Whatever we get at the bottom of that column, we multiply it by that negative 1 out front, and we add it in the next column. And we do that over and over and over. And what we're going to end up with here is we're going to end up with a remainder, as we expected, of 0. And so now the coefficients of the other than the 0 would be the coefficients of a degree 4 polynomial. And so what we know is that x plus 1 is a factor, that x equal negative 1. When we set that equal to 0, we get x plus 1 equals 0. So that's why x plus 1 is a factor. Now let's try that again. Let's see if that's a double root. And so we're going to now apply the same thing, the negative 1, do the synthetic division again now with 1, 1, negative 2, 2, and 4. Remember that 0 is just the remainder, so that's not significant as far as any coefficients. And so we always start with just adding 0 in that first column. 1 times negative 1 is negative 1. Add that up. We get 0. 0 times negative 1 is 0. Add that up. Negative 2 times negative 1 is 2. Add that up. Carry that on over and over. And what we get now is we get a remainder of 0. So what that means is that x plus 1 is a factor again. That should say the word factor. And so what that means is we have a double root of negative 1. And so that's significant on the graph, because what that does is it means the graph is going to come like a quadratic just around that point and either touch it from above or from below. So we have most of the roots. Let's continue that now with looking for another one. So we try negative 1 again, just to see if that works. It's an easy one, and so we're going to give that a go again. And so if we do the synthetic division with the negative 1 a third time, what we find out in this case, remember that 0 is just representing the remainder, so don't use that last column there, is that it gives us a remainder that's not of 0. So that is not possible. So remember here that we had, from Descartes' rule of signs, that we had one positive root so far and two negative roots. So what I'm looking for is I'm looking for a third negative root. There has to be a third negative root based on the possibilities that we listed earlier. And so let's try negative 2. The only other option we have really is negative 4. But negative 2 works. When I go ahead and I do synthetic division with negative 2, 1 times negative 2 is negative 2. Add that up, negative 2. Negative 2 times negative 2 is 4. Add that up, we get 2. 2 times negative 2 is negative 4. And when you add that to 4, you get 0. And so finally we have it down to a quadratic. the first term is an x squared term, the next term is an x term, and the last term is a non-x term, or an x to the power of 0 term. And so because negative 2 is a root, that means x plus 2 is a factor. So we have x plus 1 as a double factor, we have x minus 1 as a factor, and now x plus 2 also as a factor. So writing that in factored form, it brings it all down to this. And so the last piece we have to solve is this x squared minus 2x plus 2. Now remember that we could have 1, 3, and 2 and 6, or 3, 3, and 0 and 6. And so it's one of those two options. So it's either going to have another two positive roots, or it's going to have two complex roots. Now this is not factorable, so what we have to do is we have to use the quadratic formula in order to solve this. So quadratic formula, negative b plus or minus the square root of b squared minus 4ac over 2a. Great songs to memorize that if you ever want to. Let's go ahead now and substitute in those coefficients. B is negative 2, A is 1, and C is 2. And we divide that all by 2a. And so what we get is we get positive 2 plus or minus the square root of 4 minus 8. Now, 4 minus 8, you're starting to see, hopefully, that that is going to give us complex roots. It's going to give us the square root of a negative number, negative 4 to be exact. And we can then break up that negative 4 into the real part of that and the complex part of that. So what I'm going to do is I'm going to write that out as 2 plus or minus the square root of 4 times negative 1. 4 times negative 1. And so I'm going to pull out that factor of 4 because the square root of 4 is 2. So that's written as 2 plus or minus 2 times negative square root of negative 1 divided by 2. Now we can take that a couple steps further. The first thing we can do is we can turn that square root of negative 1 into I, because that's what the definition of I is. And then we can common factor a 2 out of the numerator and divide that out. So we get 1 plus I and 1 minus I. Those are the possible x values here. Now those are not significant on the graph because they're complex roots. They do change the shape of the graph slightly, which is going to impact like what the y-intercept is and whatnot, but they're not actually going to be zeros on the graph. So they have nothing to do with affecting the zeros whatsoever. So we're not going to worry about those. Nonetheless, our roots are 1, negative 1, which was a double root, negative 2, and then those two complex roots. Notice those two complex roots, they always come in pairs. So what this becomes is what we had above, this negative 2 times x minus 1 times x plus 1 squared times x plus 2. And then we're going to then add these two imaginary roots to that. So this is x minus 1 plus I and x minus 1 minus I. And so we could get rid of those brackets inside, but still, that is what it is in factored form. As I said, those are not affecting the x-intercepts, but yet those are imaginary roots. So the last things we want before we put this on the graph is we want to figure out what the y-intercepts are. In fact, there's only one. The y-intercept is when x is equal to 0. And we can see that when I plug 0 into the equation, all those coefficients end up being times 0. And so you just have this 8 at the end. And so that means that the y-intercept is 8. The other thing we want to consider is the end behavior. And so the first thing to note here is that it is an even function. And so because it is even, it is starting on the top to the top or bottom to the bottom. And the other thing to note is not only is it even, but it is also has a negative leading coefficient. And so because it has a negative leading coefficient, what that means is that it must be opening down. And so if it opens down and it's even, then it's going to look something like this to this. And so that means it's going to go from quadrant 3 to quadrant 4. Quadrant 3 to quadrant 4. So now let's put all that together, the y-intercept, the end behavior, and the roots, and graph this as we wrap this up. So the first thing I'm going to notice is the y-intercept. The y-intercept is 8. And so that's done. We've checked that. We also know that the end behavior means it's going to go from quadrant 3, which is down here, to quadrant 4, which is down here. And so we'll include that once we figure out how the roots fit in a moment. So we have a root at positive 1. We have a double root at negative 1. We have a root at negative 2, and then those 1 plus I and 1 minus I, these are not x-intercepts. So they're not going to have any bearing on what we're trying to graph here. So they are roots, but not something that is affecting the x-intercepts. So what we can do is we can recognize that because it's starting in quadrant 3 somewhere down here, it's then coming up through -2, and then it has a double root at -1. And so what that means is it's going to touch it like it's a quadratic right in that zone here. So it looks like a quadratic right at -1. It doesn't go through, but it bounces off of. It then goes all the way up here to +8. And then just because of symmetry here, it's not symmetrical rather, it's going to probably go a little bit higher up. That's not really relevant to what we're doing here, how high up that goes. But it's going to go a little higher up and then come back down, go through the point at 1, and then straight back down again. So we have 1, 2, 3, 4 x-intercepts, and then those two other roots don't mean anything as far as x-intercepts. And so that's the entire graph of this. We're going from quadrant 3 to quadrant 4. It has a y-intercept of 8, and it has those 3 x-intercepts, one being a double root. And so there you go. That's how you graph f of x when you have something that is degree 6. And it's the same idea for any degree of function, provided it's a polynomial where you don't have a rational function. If you do have a situation that you're trying to graph that does have a rational function, you want to check out the video on the left. The video on the right is an excellent video about how to prove trigonometric identities, which is something you're likely to see later in the course that you're taking on this topic. Thanks so much for watching. If this was helpful, I'd love a comment below. Feel free to leave any questions that you want me to look at in future videos, and have a great one.